Human civilization has achieved some incredible things during its short reign on this planet. Technological development over the past 5,000 years of human civilization has led our species to dominance of life on Earth and placed us on a pathway to achieving a Type 1 civilization. To reach even the basic level of a Kardashev Type 1 civilization, we must do two things: develop more advanced technology and share it with all responsible nations. Make renewable energy accessible to all parts of the world. 500 years ago, the Aztec civilization believed that the sun and all its power was sustained by blood from human sacrifice. Today, we know that the sun, along with all other stars, is powered by a reaction called nuclear fusion. Scientists and engineers have studied the sun's fusion process in hopes of developing a way to harness energy from fusion in machines on Earth. What exactly is nuclear fusion, and how does it work in terms of producing electricity? Professor Dennis Weitz is director of the Plasma Science and Fusion Center at the Massachusetts Institute of Technology. He explores the challenges in nuclear fusion and explains how the fusion energy can be realized here on Earth.
So fusion is simply the power source of the universe. So as you know, we have a lot of challenges around energy and how we make clean energy in a sustainable form. And the way I say is the universe is already voted. Fusion is actually the power source of the universe because almost every energy source we use is actually fusion at its core. Solar power is fusion because it comes from the sun. Wind as well too. Actually, oil and petroleum is also fusion power because it's just basically stored solar power far beneath the Earth. And stars work by the fact that they're very large balls of hydrogen, the most abundant element in the universe. And they basically convert that hydrogen into helium to make energy. And we know how effective an energy source it is. It lasts for tens of billions of years in our own sun. On Earth, the idea is that we bring it down to Earth as a sustainable terrestrial energy source. And what we do is we take the heavy forms of hydrogen, the deuterium and tritium, we fuse them together, they release net energy as a result.
Over billions of years, the gravitational forces at play in the universe have caused the hydrogen clouds of the early universe to gather into massive stellar bodies. In the extreme density and temperature of the stars, including our sun, fusion occurs. Located a mere 93 million miles away from our planet's surface, the sun is a thermonuclear fusion reaction. Without fusion, there would be no life on Earth. It is the energy source of the universe. Every second, our sun turns 600 million tons of hydrogen into helium, releasing an enormous amount of energy. It continuously batters the Earth with 35,000 times the amount of energy required by all of us who now use electricity on the planet. Imagine if we could harness the same power source the sun uses to solve our energy problems. If nuclear fusion can be replicated on Earth, it could provide virtually limitless, clean, safe, and affordable energy to meet the world's energy demand. The effort has sometimes been likened to building a star on Earth.
All stars are above 5,000 degrees. So everything's in the plasma state. Plasma is the fourth state of matter. And what happens, you go from a solid to a liquid, and you get it hotter, liquid turns into a gas. And when you get above 5,000 degrees, then everything turns into a new state of matter. It's called plasmas. The problem is, so why is this hard? Because what happens in a sun is that in order to get it hot, you need a containment system. And the containment system of the sun is its own gravity. It's just its own mass. So at the center of the sun, it can basically hold itself. But gravitational force, it turns out, is a very weak force. It's the weakest of the natural forces. And we replace this with another force that we can use on Earth, and it's actually much stronger because it needs to be contained in this. So what does this mean? Well, we actually replace that force with a magnetic force. And what this means, the characteristic of a plasma, is that it's gotten so hot that actually the individual atoms, like the atoms in this room, get pulled apart, and they have separate charges now of negative and positive, equally balanced to each other. So we exploit this force called the Lorentz force, which is a magnetic field, which forces the plasma particles to basically execute loops around the lines which are there. So what it says is that a larger magnetic field means a larger force and a better containing force, and that both electrons and ions are confined because both negative and positive particles are confined. So how do we do this on Earth? We build a system that looks like this. Because you say, well, how can you hold something at 100 million degrees? You can't. In fact, if you try to hold it, what happens is the plasma just gets cold. And it sounds dangerous 100 million degrees. It's the opposite of dangerous because it actually doesn't want to stay hot. So you basically trick it into not knowing it's on Earth. It thinks it's a star. So you build a containment system that is built out of electromagnets. And how do you do so? That magnetic force comes from an electromagnet. An electromagnet is simply you take electricity and you put it in a loop, and it's going to make that magnetic field. Why is this important? It's because the thing that's making the force is doing it without physically touching it. It's an action at a distance. So these electromagnets actually have no idea they're confining the plasma, and the plasma has no idea it's being confined by the magnetic field by these electromagnets. It just feels it like this.
Nuclear fusion reactions power the sun and other stars. In a fusion reaction, two like nuclei merge to form a singular, heavier nucleus. The process releases energy because the total mass of the resulting singular nucleus is less than the mass of the two original nuclei. The leftover mass becomes energy. Einstein's equation, E equals mc squared, on the most basic level, says that mass and energy can be converted into each other, which explains why this process occurs. So, why don't we have nuclear fusion power yet? This is an extremely powerful but complicated phenomenon, which can involve many different elements in a periodic table. However, researchers working on fusion energy applications are especially interested in a deuterium-tritium DT fusion reaction.
Well, so deuterium is naturally occurring. Tritium has a very short lifetime, and so it decays in nature. There is no tritium source. This doesn't sound like a good energy source. There's no fuel source. So the thermal neutron interacts with that lithium, makes tritium, and then you take that tritium particle and you recycle it and you put it back into the plasma. So it's a fuel system that actually creates its own fuel. I know that sounds like cheating, but that's actually because it's the wrong way to describe it. Tritium is not the fuel of fusion, it's the catalyst of fusion. So it's the equivalent of what you would have in a chemical reaction. So in the end, it's very interesting. What are the consumables in fusion? It's deuterium and lithium. And lithium is so abundant, it's essentially an inexhaustible fuel source. That sounds way too simple, but you gotta remember those fundamentals are there. It's why we pursue fusion. At its heart, it has physics advantages that are just almost insurmountable to overcome. It turns out it's practically hard to make this work, but we're getting closer. So what do we actually do? Well, so it turns out you have to make like outer space. This occurs in a hard vacuum. You eliminate all the other particles away from there. So in a hard vacuum, you've got to put materials around this because you're going to make this exotic fuel because it's got to capture the energy. Oh, but this neutron is going to knock the heck out of those materials. So those neutrons actually alter the surrounding materials in a fundamental way. It actually can do that. And then inside of this, it also alters the interior surfaces because it's like putting things on the surface of the sun.
DT fusion produces a neutron and a helium nucleus. In the process, it also releases much more energy than most fusion reactions. Researchers focus on DT reactions both because they produce large amounts of energy and they occur at lower temperatures than other elements. The current leading designs are the tokamak and the inertial confinement by laser. Both designs are under research at very large scales, most notably the ITER tokamak in France and the National Ignition Facility laser in the United States. The possibility of harnessing energy from nuclear fusion in the 21st century by using large-scale nuclear reactors is met with a degree of doubt by many scientists, who question whether the enormous engineering challenges associated with such a project have been correctly estimated. That is why the MIT Plasma Science and Fusion Center is developing a conceptual design for a compact, high-heel net fusion energy device dubbed SPARC. SPARC would be the size of existing mid-size fusion devices, but with a much stronger magnetic field. There are now more than 30 private fusion companies globally as well. Despite their powerful tools and creative approaches, many of these new ventures will fail. But if just one succeeds in building a reactor capable of producing electricity economically, it could fundamentally transform the course of human civilization. Thanks for watching. Did you like this video? Then show your support by liking, subscribing, and ringing the bell to never miss videos like this.